All right, welcome ladies and gentlemen to section 2.6. This is our last section from chapter 2, and what we're going to be doing is finding inverse functions. So let's go ahead and move on to what they are. So there's a couple things as to what they are and what they look like mathematically. The first thing is an inverse function is something that undoes another function. In most of our algebraic cases, multiplication and division are inverse functions because they undo each other. Addition and subtraction are inverse operations because they undo each other. The square and the square root, they undo each other. If we were to think about these things graphically, like the square and the square root function, this is the square root function, and this is the squaring function. They actually reflect across the line y equals x. If you're given a function f of x, we note or denote that the inverse looks like this, f negative 1x. This is actually read f inverse of x. Whenever you see this negative 1, kind of like an exponent, this is f inverse of x, or the inverse of the original function. This is not, and I stress, this is not a negative exponent. This does not equal 1 over f of x. If you write that, you automatically get the problem wrong. So you must make sure that you do not think that. This is f inverse of x. So let's look at how to do this algebraically, how to do this with pencil and paper. Your very first step, you must swap the x and y values in your equation. We are going to use our simple math, addition, subtraction, multiplication, division, square roots, all that sort of stuff, to resolve for y, or get y by itself again. That new equation that you get is the inverse of the original function. So let's think about f of x is equal to 2x plus 3. This is the same thing as saying y equals 2x plus 3. To find the inverse, we need to swap x and y. That's my first step. And now we need to solve for y. So we're going to subtract 3 on both sides and divide by 2. That is f inverse of x. This is our new inverse function, 1/2 x minus 3/2. Well, what about this one? We have the function y equals, or the equation y equals 5 minus 3x all over 2. We need to swap x and y. Now we need to multiply by 2 to get y by itself again. So multiply by 2 minus 5 don't forget your negative 3y there, and divide by negative 3. So y is equal to divide by negative 3, divide by negative 3, and we get negative 2/3 x plus 5/3. This is f inverse of x. What about the cube root? So we get y equals the cube root of x plus 1. Well, swap x and y. In order to undo the cube root, you must cube both sides. So I get x cubed is equal to y plus 1. I need to subtract 1. Therefore, the inverse is x cubed minus 1. That's my inverse function. I have one more that I'm going to do that I didn't write down here. I don't think I did. Okay, so let's say we had the equation y equals x minus 1 over x minus 2. This problem gets a little bit challenging here. We need to swap x and y, so we get x equals y minus 1 over y minus 2. This is going to require some cross multiplication, so we get x times y minus 2 is equal to y minus 1. Doing my distribution here, I get xy minus 2x is equal to y minus 1. Now, since I'm trying to solve for y, I need to get y by itself. So I need to get all my y's on one side. So I'm going to subtract y, and I'm going to add 2x. And I get this new statement. Then, because both of these terms have a y in it, I can factor out a y. And I need to divide by x minus 1. And there we have our inverse to x minus 1 over x minus 2. Okay, moving right along, we can look at some stuff graphically as well, mainly looking to see if a function has an inverse. If you were to graph a function and wondered, hey, does that function have an inverse? It does, if and only if the graph passes the horizontal line test. Meaning, if I was to give you a function that looked like this, if I drew a horizontal line anywhere on this graph, that horizontal line would only touch once. That means it passes the horizontal line test, which means it does have an inverse. But there are times when some problems, let's say this quadratic, does not pass the horizontal line test. So this would mean this particular function has no inverse on its domain, but what we can do is we can limit it, and let's say only the domain of these positive pieces here. And if this was the only part of the graph, then it would have an inverse. And like I said earlier, graphs of inverses are reflected across the line y equals x. Basically saying, if you had x comma y on the function, its inverse would have y comma x. So this would be on f of x, and this would be on f inverse of x. All right, last little thing here is a couple properties. If you were to compose doing f of g or f of f inverse or f inverse of f of x, you will always be able to simplify down to x if they are inverses of one another. That's how you can actually prove if two functions are inverses of one another. If you simplified it, you would get x as a final answer. And last two things here is the domain of f of x is the range of the inverse, and the range of the original function is the domain of the inverse. And that really comes from the fact that we switch x and y. So the x's become the y's and the y's become the x's. All right, that's going to finish us off. Nice, easy lesson to finish off the chapter 2. Hope you guys learned a little bit of stuff. Hope you guys do your assignment, and I will see you guys tomorrow.